Okay, if you have not read through the slides and watched the video contained in the slides, please do so before you start watching this because it will make far less sense. The slides highlight the important bits. The video gives you an overview of what a linked list is. So I'm assuming you know what a linked list is. I'm assuming you understand what a node is. We're going to implement a doubly linked list with this one. I'll just call it double list. I make the node static because it doesn't depend on the list itself. It's just a part of the list in that you can't have a linked list without a node. But the node itself doesn't care about the actual linked list. If you didn't make it static, the node would basically have an internal reference to the list it's in, and it really doesn't do that. This string, actually no, I'm making that. There's no need to make a constructor inside of an inner class public or anything. You can make it private if you wanted to, but I just don't bother making anything. So that's the essential bit of a node. We could even take this class and make it an external, a top-level class, just the node, and then make a subclass of it in here, but we're not going to bother with that. But you could, because lots of different data structures use nodes. This is the basics for all of those nodes. This is probably shouldn't be final, because you may want to go through and change the value of a node at a later time. I don't know that for sure, so my general rule of thumb is if I don't know it, I'll make it final. But this one I anticipate that I'd like to be able to change it. I probably won't change it in the context of this demo though. So consider a node to just have two pointers. I call them references. One's next, one's previous. So it points to where it is. For any given node, it will know the one that comes after it and the one that came before it. And we'll see what has to change in the constructor later. Quite often, always, you'll have a head, which is a node. Quite often you'll have a node which is a tail, especially if you're dealing with a doubly linked list. So the head points to the very first node in the list. The tail points to the very last node in the list. Notice they're not final because what happens if you removed the very first item in the list? The new head becomes the next item in the list. Can't actually think of anything for the constructor, so I'm going to leave this here for now, but it probably just goes away shortly. Okay, so we want to add something to the list. If the head equals null. Just pause for a second because actually when my son had to implement a linked list, I gave him a suggestion. This will save you so much time. So if the head equals null and the tail not equal to null, right? If the head is null, that means there's nothing in the list. So if the head is null, the tail must also be null. So I'm just going to basically make a few tests in here to check the state of things. right? So if the head is null and the tail is null, then we've got a problem. Sorry, if the head is null and the tail is null, we're good. If the head and tail both aren't null, that's good. If the head equals the tail, if they're literally the same object, that's perfectly valid. So we don't have this thing called a count, so I'm going to make another variable called count. So the head is equal to the tail, and then the count has to be 1. That's not necessarily true. It has if it's greater than 1. Actually, in here, if the count is less than 0, that's impossible. You can't have a list that contains fewer than 0 items. Right? So if our count somehow gets less than 0, that's bad. If the count is greater than 1, and the head and tail are equal, that's bad. We could change this a little bit though. If head equals null, and head equals tail, and the count is not equal to 0. So it's already checked that above, so I don't need to be that explicit. So if the head equals null and the count isn't equal to 0, so the count should be 0, and it isn't. And if the head is not equal to null and the head equals the tail, and the count is not equal to 1, right? So this is just all the things we need to check, right? So, if one of these is null, they both have to be null. The count can never be less than 0. If the head and tail are null, then the count has to be 0. And if the head and tail are equal to each other, then the count has to be 1. And I guess there's one last check, just to be sure. Right, so if the head is not null and the tail is not equal to the head, then the count has to be 2 or more. So that kind of is a sanity check for everything. So at the end of this function, we're going to call that. Basically, the end of all of the methods that modify the list. That's actually just do it for all of them. But it's just a quick sanity check to make sure things are working out correctly. We could then choose to comment that out later on once we've got everything debugged. But this will help us immensely while we're implementing the list. So no matter what, we're going to make a new node. Just to cause extra confusion, I call the new node new node. And then it's hard to say when I'm speaking if I'm saying this new node is assigned new node. And we need to pass in the value. I don't do that to be confusing, but new node is the most sensible thing. So you'll notice I say new node versus new node. There's that pause. So make a new node and put it in there. If we wanted to, we could call that temp node, but it's not temporary, it's permanent. So if the head equals null, we're going to make the head point to new node, and we're going to make the tail point to new node, and we're going to make the count, well, we can just increment the count. We could do unit testing, and we should do unit testing, but I'm also going to show you just a simple little way to do this too. So first off, my list.size problem is we don't have a size method. And here the size should now equal to 1. Right? You can see how this looks very much like a unit test. Actually, I put that up above. So let's give this a run and see. Finished with no errors, so we're good. Well, good for what we've tested so far. So now let's call list add 20, and the size should equal 2, right? We've added 10, we've added 20. This should throw an error. Right, and it's telling us here that this happened, so our list size isn't correct, so why isn't our size correct? Well, size is correct, it's pretty simple. So the problem is we're not incrementing our count. Well, we could fix that. We could do this. We can say every time we add a node, we're always going to increment the count. There's no need to do it over here. We just deal with that. So now let's see. And we got a problem that the count should be 1, but it's 2. So when does that occur? Well, that occurs when the head is not equal to null and the head is not equal to the tail. That's not right, because we've only done, the problem is we've only done one thing, right? We've only added in the case that the head is null. So now we have to actually do the next piece. So in order to do this next piece, we need to go from the beginning of the list all the way to the end. But we don't, because we have a tail. So this is where the doubly linked list comes in. So the tail is now assigned a new node. And it really helps if you have a piece of paper. And I don't know how to actually draw on a piece of paper and show this video, so we'll just see what it looks like. So here's a node with 10. Actually, head is pointing to 10. And tail is pointing to that too, right? So that's where we started with. So now what we've got is our new node. It's pointing at 20. What we want to wind up with at some step is head is pointing to 10, which is pointing, I'll do it this way because it's the doubly linked list, points to 20, which is pointed to by tail. So if I'm going to add to the end, I always need to say that the new node dot previous is assigned tail, right? So that will have this. That will leave us with head is pointing to 10 and 20 is pointing at that. I don't have a good way to do this, so I'll have to do it this way. The tail is also pointed to 10. I don't have a way to draw that up arrow, but there we go. So our head is pointed to 10. Now that we've said new node, previous is pointed to the tail, right? So new node is previous is pointing to the tail. Now what we need to say is that tail dot next is pointing at new node. It really helps if you have a piece of paper to literally draw this stuff out. So it was 3. So this is 4. Now we have, I'll just actually I'm going to copy this. And now what we have is that part. Oop, that part. Right? So new node's previous is pointing at tail. And tail's next, this is tail, right? Tail's pointing at this. Tail points at that. Tail's next is pointing to that one. And now the last thing is to set the tail equal to that one. So it takes 5 steps. Let's run it and see. That's good. But we don't actually know if we're putting them in properly. So let's do this. Int public int get at final int index. And now you're about to find out why linked lists are truly slower than arrays, and why we want to use array lists instead of linked lists. But linked lists are quite handy for inserting into random order, or when you don't know how large your array is going to be, for example. Primarily that idea of we're going to insert into any random order into the list, which is a very uncommon thing. But when you do that, that's when you use a linked list. Other than that, use an array list. So we need to do a for loop. For I is assigned 0, I is less than index, I plus plus. One thing, we can shortcut part of this. We can say if the index is greater than count. Now, think about count. Count starts off at 0 if it's empty, and 1 if it's got one item in it. So when we pass in the index, we're going to pass in, we want 0. That's the first item in the index, or first item in the list. So 0 is the first item in the list. When the list is empty, the count is equal to 0. So if 0 is greater than count, 0 is greater than 0, that's not correct. It's count minus 1. Right? Because we have to take into account that empty list. So 0 is greater than minus 1 on an empty list. We're going to throw it must be less than. Or equal to? I think that's correct. We'll find out later on if that's correct. I'm not going to overthink it right now. We'll make an example where that happens. So what we need to do is we need to start at the... And there's a couple of optimizations we can make, but we can worry about that later. So we're going to start at the front of the list. So we're going to need another node. And the idea is that we're going to navigate using that temp node from the head all the way to as far as we're supposed to go. And then we're going to return the temp node dot value. So we're going to use this to go all the way through the list, this for loop, until we reach the node we want. And I'm not going to bother with that right now. What I'm going to do is just here, we're going to get the 0th item. Sorry, it's not get, it's get at. Right, so we're going to get the 0th item out of the list. Here we're going to get the 0th item and the first item. So it should print out 10, then it should print out 10 and 20. It's not going to, it's going to print out 10, 10, and 10, but we'll fix that. Let's just make sure this works to begin with. Okay, like I said, 10, 10, and 10. And we can just double check to make sure here, before we do the add, that, right, oop, I mistaken my phrasing here. Right, so the index has to be less than or equal to -1. It was 0. Oops. Right. If we come in here and we put in a 1 here, where we've only got one item in the list, and we're asking for the first item and the second item, this should say it has to be less than or equal to 0. Yeah, so there we go. So my message was correct. That's good. So the only problem now is that we're not actually getting the second item out of the list. So we started head, right? Remember, we've got head is pointing to 10, which is pointing both ways to 20. Right, if we added another one, it would be 30, for example. Right, so there's a list that has 10, 20, and 30 in it. 20 points to 10, and 20 also points to 30. Technically, this points like this too, because 10 is pointing back to null. So it's a little misleading though. So we'll just leave the last ones where it knows that it's pointing to null. So I don't have a really great way of showing that here. But the thing after this, were to do it like this, I guess. So I don't have a really great way to. Oh, I did that. Don't have a really great way to show that on in comments. So it's 30 points to null, and the tail points to 30. 10 points to null, and head points to 10. So the problem here is that we're not looking at the next thing. Now that you want to do something like temp node plus plus. But that makes no sense here, right? Because that's incrementing a memory location. This memory location could be memory location 1, this could be memory location 1000, and this could be memory location 236, right? There's no rhyme or reason to where these memory locations actually are. So we can't do plus plus, so it doesn't make any sense in Java. That kind of thing makes sense in C, but also doesn't make sense for linked lists in C. So what we want to say is temp node is assigned the temp node next. Right, so we have another thing here, which is temp node points to 10 to begin with, right? And now when we say temp node is assigned temp nodes next, that means we go to 10s next. So temp node is now pointing to 20, right? And then it points to 30, and then it winds up pointing to null. So that's how you iterate through a linked list. So we're going to do that I number of times, right? And we already know that we've got the right size because the count is already checked up here, right? If we're trying to walk past the end of the list, it won't work. So let's see now. 10, 10, 20. Yay! So let's go ahead and add 30, just so we had that example in there. So we're going to add 30. And we're going to get index of 2. Oh, I could do a better job. Let's do the checking of the size before we call the things. Just makes makes a little bit more sense. I will post this code. Okay, so now we've got 10, followed by 10 and 20, followed by 10, 20, and 30. So our add works. Awesome. And if you only had a singly linked list instead of a doubly linked list, where you didn't have the tail, and you didn't have the previous, then you would notice that not notice. You would you do the insert the same way, right? Here we're able to shortcut it because we have the tail. But if you didn't have the tail, then you'd have to start at the beginning of the list and go up until the next one was null, and then add it to the end. That's it for that one. I think add is completed. So get is completed too. So let's do remove. Keep it consistent. Remove at. Now this is almost the same. Now I'm removing the int just so we know the value that was removed, right? So if we remove from 0, we're going to return 10. If we remove from 1, we're going to return 20. If we remove from 2, we're going to return 30. So it's a useful bit of information. So again, we can't remove past the end of the list. That's fine. We need the temp node to navigate to the appropriate place. Now this is where things get a little more tricky. So we're good with this. The problem is now we want to remove things. So back to our thing. So we'll say we've got head, which points to 10, which points to 20, which points to 30. Right? So let's say we want to remove the first one. Right? How do we go about doing that? We also have temp node. So it's pointing at 10 to begin with, right? Temp node is assigned head is looking at 10, so temp node is looking at 10. We've gone 0 times, we passed in 1, so we're going to advance the temp node. So temp node now points to 20. And that's, we're moving 0. So, sorry, going too far ahead. Actually, let's go ahead and remove 20. So we'll say we're going to remove 20. So we're going to remove the index of 1. So now we're at 20. Awesome. How do we do this? What we want to wind up with ultimately is that, right? That's where we're heading towards. And again, drawing these things with pictures on paper, just drawing it like this, makes life so much simpler. So what we have, and we also have temp node equals 20 at the moment, right? And remember that 20 is pointing at 10, and 20 is pointing at 30, right? So that's the information we have, right? And we want to make 10 point to 30 and 30 point to 10. And then we've removed the item. So it's actually really simple. All we have to say is that temp node dot next is assigned. So the 10 is assigned 30. Sorry, temp node's previous. Right? Temp node's previous gets us to 10, and we want it to point to temp node next. Now 10, sorry, that should be there. Now what we have is temp node 10. This one is pointing back, 20 is pointing back to there. These ones are pointing like this. Okay. And we also have this one pointing over here, right? So 10's next is pointing there. So now what we want to do is the same thing. We want to take this and now make it like that, right? So now we want 30 pointing at 10. So to do that, we'd have to say that the temp node 20, its next is pointing to temp node's previous. So 30 points at 10. And if we really wanted to, we do not need to do this at all. We could say temp node dot next is assigned null, and temp node not previous is assigned null. You don't have to do that. The garbage collector will deal with all this. So temp node's not being pointed to by anything after this, so the garbage collector is free to free it up when it wants to. So now we're going to turn the temp node value. And our size, our count, needs to be decremented. Right? So if we come in here, and now let's actually try that. So we're going to say list dot remove at, and it was index 1, right? Index 0 is 10, 20, 30. So we're going to move the 20. So our list should contain of 10 and 30 at the end of this. The count should now be 2, and this should be 10, and this should be 30. And it's 10 and 20, which doesn't seem right. So something went wrong. So simplest thing here is to so temp node dot value and just say removing this. So we're removing 20, so that's correct. So let's see. We're going to put a breakpoint in here, and we're going to run this in the debugger now. And we can actually see what it looks like. So that one's pointing to 10, and that one's pointing to 30. So that makes good sense. And I need to, there we go. I need to step over. So now the temp node previous wait a second. Yeah, that's correct. It's temp node's previous. Okay, there's a temp node's previous should not be equal to 30. Temp node's next is 30, and temp node's previous is 30. Well, that's not right. So I suspect it's actually, we just didn't catch it. When we did the add, we didn't properly deal with the add. So let's come in here for a second and take a look what goes on. So our new node is 20, and it's got next and previous of null. And then we're going to step over. And its previous is pointing to 10, good. And the next is pointing to null, which makes sense. But I think that's all that we've forgotten. No, that's correct. So let's continue on. Again, drawing pictures really helps. Sorry, the menu changes on here. I don't know the specifics. There we go. Menu changes on my Mac. So our new node is 30. Next and previous are null. The head is pointed at 10. Its previous is null, and next is 20. Its next is null, and its previous should be 10. Yeah, that all makes sense. So the new node's previous is tail. Which is 20 at the moment, yes. And then the tail is assigned new node. So the tail has a value of 30, its next is null, and its previous should be 20, and it is. So that makes sense, and its previous should be 10, which it is. So that's correct. So here, our temp node is pointed at 20, the next is pointed at 30, and the previous is, how does the previous point at 20? So let's put our breakpoint here. Stop this, run it again. Okay, I guess I got rid of the breakpoint before now. No, I want to debug it, that's what's going on. And I don't want to stop it here. Okay, so our heads, next, right? It's 10, 20, 30. And then if we look at the tail, it goes from 30 to 20 to 10. So that's all correct. So that part's all good. So it's something else that went wrong. I think I was just looking at the wrong thing when I did that, actually. Temp node's previous is 10, temp node's next is 30. Good, well you learned to use some of the debugger. It was just that I was hitting previous here. So it is correct. Okay, good. So that part's good. So the temp node's previous is now assigned sorry, the temp node's previous is next. Temp node's previous next is assigned null, which should not make sense. So we'll come back, set the breakpoint here, run at the debugger. So our temp node, we're going to look at this here. The temp node, its previous is 10, and its next is 30. So here, we're going to say temp node's previous is assigned temp node's next. So temp node's previous is pointing at 10. So the temp node's, my mistake here, that's where I made my mistake. Temp node's previous next is assigned next. Temp node's next is assigned previous is, temp node's next dot previous There, that'll do. My code didn't match my diagram. Now this may crash, it may not. It should be fine. It'll crash eventually. So there we go, 10 and 30. Right. So again, it's just I did the previous instead of the previous is next to make that happen. If I actually drew the picture instead of trying to do it with comments, it would have caught it. But the debugger is useful. So this is awesome, but let's change it to be, instead of that, let's remove the first item. So now when we remove the first item, we should still have 2, and we should get 20 and 30. I think this will crash. Yes. So the problem here is that we're head is 10, right? Then we've got this, and then we've got this. And then we've got null, which is being pointed to, and then we've got null here, which is being pointed to. So this is the state of our list, right? I should probably just keep this as a comment. So what we're here is we're at 10. So temp node is pointing at 10. So our code here says temp nodes previous, so temps previous, which is null dot next. We can't do that, right? Because then we're saying null dot something, right? So here we have to special case it. If temp node dot previous equals null, else. So if the temp node's previous is null, all we have to do is say that the head points at the head.next. Right? So all we're saying is now that head will now point at that instead. And that means that we also have to adjust heads next to null, or the new heads previous has to point to null, right? So 20 needs to point at null. So that also means that in here, head.next equals null. Otherwise, we'd still be pointing at 10. So if we're going back from the tail, we'd still have 10 in our list. So this prevents that from happening. So let's see if this works. Still getting a null pointer exception. That's just really weird. Oh, the get. So I obviously haven't finished setting something up yet. So the head points to the heads next. Heads next points to null. And we were calling get at 1. So again in the debugger. So temp node is equal to 10, and its next should equal to 30. So that's odd. So let's take a look at what happens when we get to here. Yep. That should be this. Sorry. Again, I don't know the shortcut to continue, so I'm just going to have to run it again. So temp node is pointing at 10, which is correct because this is where we are doing the remove at. So now head points at 20, head's next points at 30, and head's previous points at 10. And I said head next, I meant head previous next. There we go. So that worked out fine. So let's try getting rid of the item at the end instead, because that's probably going to have a problem when we do something at the end. Yes. Sorry, 2. I'm still expecting a crash though. Yes. And it's the exact same thing, except it's the obvious. So obvious is the opposite. So here, now the temp node's next is null, right? So we're trying to remove from 30, which is pointing at null. So if the 30 is null, what we're going to do is change the tail. So the head, it's the head's previous, and this is the next. And this should be fine. Nope. Same sort of problem. So what have I done wrong? So this one works. It's this one that didn't work. So the tail is assigned the head's, not the head's previous, the tail's previous. And this should be tail dot next is assigned null. There we go. So now I've got 10 and 20. So there's only one more thing that's probably going to cause this a problem. Let's try a couple of pathological things. So let's just start this whole thing over. I'll just comment this code out for you. So first, let's see what happens if, well, we want the size to be 0, yes. Let's see what happens if we call list.remove at 0. This should throw a legal state exception, or illegal argument exception, right? That -1, okay, good. So now let's add 10. So this is the other weird case, which is what happens when we remove the head and the tail, right? There's only one item in the list. So there's a null pointer exception, and it's here. So we can do one more thing. If count equals 1, right? Special case. We could also say if the head equals the tail. Either way. What we have to say here is head is assigned null, tail is assigned null, right? So the count is decremented, yes. So we're making it so that there's nothing in it; it's empty, right? Notice we don't have to do anything special at all. What's it unhappy about here? There should be else's, because they're meant to be special casing. Right, so if the head equals the tail, then we set it to null. If and the tail is to null, and we're good. If there's we're removing the first item in the list, so this is removing only item. This is removing first item. This is removing last item. And this is removing any other item. Okay, so there's a few special casings we go through. So let's see. Shouldn't crash now. Yay. So we go back to, and then we want to make sure that the size is 0 again. Yes, good. So cool. We've got stuff happening. We also should probably remove this system.println. We don't need it anymore. So that's the adding and removing. The other thing we could do is to do, which is very similar, is find. Now here we're actually going to look for the first occurrence. We will call this find first. We'll do two of them. We'll do find first and find last. So this is going to find the first occurrence of a given value. It's again very similar to this code here. Not exactly the same. It's very similar to get at. First off, we don't need to worry about the index because we didn't pass it in. And it's going to return the index where it was, or we'll say it will return -1 if it didn't find it at all. So we can't do a for loop like this anymore. What we have to say is, well, temp is not, temp node not equal to null. We want to check to see if temp node dot value equals the value passed in. We're going to break. I'm not returning the temp node value to actually return the index. Well, now we need a variable for index. Set the index to -1. And here set the index to position. What on earth is position, you might ask? Well, position is the position in the list so far. And here we can do position ++. Right, so we're going to start off with index being -1, and we're going to go with the temp. Well, actually, I'm going to run this in the debugger so we can actually watch what happens. So let's go back to here. Let's actually make one more method just to make things a little nicer for us. We're going to add a special method called clear. Right? It's going to empty out the list. To empty out the list, you have to set the head and the tail to nothing, to null. And we're going to reset the count to 0. Yay. So now we can do list.add 10, 20, 30, 40, 50, 10. Actually, let's add 20. Right, so we've got 10, 20, 30, 40, 50, 20. And we're going to do system.println list.find first for 20. So it's going to go to the 10, not find it. It's going to go to the 20, and it'll have found it. So it should have returned an index of 0, 1. Let's just see if that works. And it does, right? Just put in another set of asterisks. So it worked. Let's put in finding of 50. So 0, 1, 2, 3, 4. Should find 4. Yeah, or return 4. So let's take a look at why that works. So the temp node is pointing at 10. Right? And temp node's next is pointing at 20. That one's pointing at 30. 40, 50, 20, and then if we go back, previous is pointing to 50, 40, 30, 20, 10, and null. Yep. So we're starting off at 10. So we're going to step over, and we're going to check to see if the temp node's value equals the value that was passed in. The value passed in was 20, so it doesn't equal. So we're going to advance it to the next one. We're going to increment our position to 1, right? So now we're at the 1 index. And temp node is not null, and we come in here, and that equals, as you can see, true. So the temp node value of 20 equals the 20 that was passed in. So now the position is going to be assigned 1. Right? So the index is going to be assigned 1, and it's great. We break out of the loop, and we return the index. Let's see what happens, though, if we were to look for 60. If we look for 60, it's going to look at 10, look at 20. You can see the thing down here, temp node value changing. Yep, that was fine because that's what we're looking for. So I'm just going to skip past this quickly. Okay, so now we're going to look for 60. So remember, watch this temp node value down here, right? It starts off at 10. Then it goes to 20. Now it's at 30. Now 40. That'll be 50. 50. Now it'll become 20. And now it'll become null, right? Because we walked past the end of the list. Remember, our list only holds 10, 20, 30, 40, 50, 20, null. And we were looking for 60. So index started off at -1. And since we never found a match, we never changed the index from -1. So it'll return -1, right? Which indicates that we didn't find it. So that's cool. Now we're going to do find last. Find last is the exact same logic, just in reverse. It's really simple. So we're going to start off the index at -1, that's fine. The position is going to start off at count -1, which is the valid indexes. We're going to set this to tail instead. And now what we're going to do is we're going to search for find last. So find last should look at 20 here and find it. Actually, let's move it here. So it should look for 20 here and find it, right? So it won't find it at the count, right? Remember the count is 1, 2, 3, 4, 5, 6. So it should find it at 5. So this should be 5. This should be, oh, actually, I can put those back because I did do that one. So this should be 6, this should be 5, and this should be -1 for 60. Right, so it's going to go 5, 4, 3, 2, 1, 0, or and then not find anything at all. So that should be correct. So the temp node not equal to none, temp node value, blah, blah, blah. We do temp node previous, right? Because we're working our way backwards through the list. And then we're going to do our position minus minus. So it's the exact same code, just slightly different. Five, 4, and 1, or 5, 4, and -1, and that should be 0, 1, 2, 3, 4, 5 is correct. 0, 1, 2, 3, 4 is correct. right? Because we're looking for the last occurrence, right? And then 60 wasn't found at all, and it's -1. Now comes the fun part. I don't want to have to redo this for, and there's no need to change this, so we'll make it final. I don't really have to redo this for float and everything else, right? So I want to actually make this generic. So that needs to become T, which means that needs to become T. But where the heck did T come from? Well, T came from here, right? Now the problem is, you see, all the nodes have to be made as T. Right? And this is letting me make a node of string or a node of integer, a node of database, a node of whatever I want. And now comes the next part, which is, well, I need to make this a node T. And this has no clue what T is. It's very simple. Add T up there. So the count, that makes sense. It stays as an int. Head and tail and all that fun checking stuff, that's correct too. The size stays as an int. We're not adding an int anymore, we're adding a T. And we're dealing with node T. And put those there. And the get at index is fine, but we're returning a T, right? So we're returning the value at that index. And we're removing at, same thing, it's returning a T. And again, we're dealing with node T, and we're looking for a T value this time instead. There's a mistake here. I'll deal with it in a second. And the same thing here, we're looking for a T. Okay, so the mistake is this, right? We don't use equals equals on objects, right? So what we need to say is dot equals. So this will now work for anything that has the equals method overridden. If you don't override the equals method, don't expect it to work. So converting the generics is simple, but you've got to remember those equals equals versus dot equals. From that point of view, it's actually easier if you started with a string instead of an int, because the string you would have already been dealing with the dot equals. So this list now is a double list of integer. Helps if you spell correctly though. Right? Which made all those warnings go away, and now I can't do something like add the string 20 because this is a 20 that's a string and it needs to be an integer. We can also now say I want to make this a list of string. Actually, I'm just going to hard brute force this string. Now all of these are not going to work, so I'm going to put in the string for them instead, just because it's easier. That. So I can paste on one side, but I can't paste on the other side. Right, so this will still work. Right, the values are all basically the same. You can see all that, right? If you go through it. So now we've got our type safe thing, converting it over to generics, and see how easy it was to convert the generics over. Normally on the final exam, I would ask you, here's the doubly linked list code, convert it to be a generic, and I would have given you all integers, and you would have to do that. Clearly, I won't be asking you that on the final now. One, I just gave the question away. Two, all you're going to do is type it in. So, that's the basics of that.